All right, in this video, we are going to talk about Riemann sums. So the question is, how do we compute definite integrals when we can't use known geometric formulas like we did in the previous example? So in the previous example, we used, the formulas for the area of a triangle, the area of a circle, the area of a rectangle to find definite integrals. But what if the graph is not like that? What do you do? Well, it was, or this idea was published in 1854 by Riemann. And so that's what we're going to take a look at. His basic idea is to approximate the area using rectangles. Okay, rectangles are simple to calculate the area of. It's just length times width, right? So we will get an approximation, and then we'll find a formula for those approximations, which will wind up to be a function of how many rectangles are used. And then basically we will take the limit of the formula to get the exact area that we want. Okay, so that's the general idea. Okay, so let's go through Riemann's scheme here. So first off is the approximation scheme. So what we're going to do is we are going to fit some rectangles in this area here. So let's say we want the integral from a to b of this function f of x dx. Okay, and in order to do that, there's no geometric formula that's going to work with that, our known geometric formula. So what we're going to do is fit some number of rectangles in there, and I'm not going to specify how many rectangles we're going to use because that's what we generally want to get a formula for. Now in my diagram, I'm only going to use 3 rectangles because my drawing will get too crowded if I use any more than that. So here's the interval that we're integrating over, the interval from a to b, and we want the area of this region in here. So what I'm going to do is to split that up into into some number of subintervals. So the first subinterval is going to go from a to whatever this is. The second one is going to go from here to here, and my last one is going to go from here all the way to b. And most people have the question, well, you don't make them all of the same length. And the answer is Riemann showed that you don't have to do that. But they do have to get smaller and smaller. In other words, the maximum width has to go to 0 the more rectangles you use. So I am going to kind of gloss over some parts like that. Okay, so in order to calculate the area of these rectangles, we are going to have to write down how long our intervals are. Okay, so I'm going to have to measure this interval out and write down its length. And now the traditional symbol for that is a delta, uppercase Greek letter delta. And since the widths of these don't have to be the same, I can't just use delta x. I have to use delta x1 for the width of the first interval here. Then delta x2 is the width of the second interval here. Delta x3 is the width of the third interval. These are just numbers, so this might be 2, this might be length 1, and this might be 3. So delta x1 might be 2 if this were 2 units across. Delta x2 might be 1 if it were 1 unit across, and delta x3 might be 3 if this were 3 units across. Whatever numbers they are, we just need to write them down because we're going to use those to calculate the areas later. All right, the next step that you need to do is you need to pick a point in each subinterval. So you're going to go over here to this first subinterval and pick a point inside there. All right, so I'm going to pick this point right here. All right, and I am going to need to write down where that point is located. So say if it were at 2 on the number line, I would need to write down a 2. So I'm not going to specify what this is because we need a formula to do that. So I am going to write x1 star there. Okay, so x1 star, again, the 1 subscript just means it's in the first subinterval. The little star there, which is like a little asterisk, just basically means that it was chosen at random, subject to some condition, and that condition is being in the first interval. All right, it is just a number, so don't worry too much about that. I'm going to go over here and pick another interval, okay, another point rather in the second interval, and I'm going to call that x2 star, and then I am going to pick a third point in the third interval and call that x3 star. Okay. All right, and so now that you have specified these subinterval lengths and picked points, now you can completely specify what the rectangles there look like. So step 3 of Riemann's scheme is to build a rectangle over each subinterval. So in this case, we're going to have 3 subintervals. If you did 1,000, or 3 rectangles. If you did 1,000 subintervals, you'd have 1,000 rectangles. Okay, so the width of each of these subintervals is the width of the rectangle. So I'm going to start building my rectangle here, and my first rectangle is going to kind of go in like this. So it's going to be sitting on the x-axis, and it's going to go towards the function. Just to keep things simpler, the drawing simpler, I just drew the function so it's up here. But if the function went down below the x-axis, this rectangle would be turned downwards. Okay. So I'm starting to build the bottom of my rectangle. You can see it here. And then I'm going to go in and start framing out the bottom of the second rectangle. All right, and it's going to be exactly as wide as I picked it here. That's important because remember I wrote these numbers down to figure out how wide it is. And I'm going to use those numbers to calculate the area of the rectangles. All right, and then the third rectangle is going to go right in here. All right. So I have the widths of my rectangles. Next up is I need to finish off the rectangles. So basically I need to know how high up should I build the rectangle. And that's what these points are going to be used for. All right, so for instance, the first rectangle, I'm going to go to where that first point that I picked. And I'm going to go straight up to the function in this case. If the function was down below the x-axis, I would go straight down. So wherever that point is I picked, I go straight up to the function, and that's where the very top of the rectangle is going to cut through. I'm going to build the rectangle right here on the top. So, all right, and so my first rectangle is going to go right through there. That also has the advantage that it is really easy to figure out how high up, what the height of this rectangle is. All I would have to do is take this number x1 star and plug it into the formula for this function, whatever that is, right? Because that would give me the y value, how high up the point is right here. All right, and I just do the same thing. For the second rectangle, I take this, right? And I go straight up to where the function is at, or down if it's down below, and that's where the top of the function is going to go through. And I have a nice neat formula for what that is. I just take this number and I plug it into the function f. That will give me how high up this rectangle is, and then I finish it off. Same thing here, right? Go up to the function, put the roof of the rectangle right through there, and this would tell me how high up the rectangle is. Okay, so all my rectangles are built, and so now I'm ready to get the approximate area. All right, so the approximate area is the sum of the areas of the rectangles. So I find the area of the first rectangle, however that is, and then the area of the second rectangle, and then the area of the third rectangle, and then I add them all up, and that is going to be the approximate area. Now you may say, hey, well, that doesn't look like a great approximation because look, you've got some areas over here that are not accounted for, right? This would be an area, part of the region that we want to find the net signed area of, and it's not counted in your rectangles. And then so you have some underlap here and some overlap here, right? This rectangle is poking out, and this is the area that we don't want in here. Okay, but I'm going to show you how this scheme, right, can be used. Using this scheme, we can get approximations that are as close to the actual area as we want. Okay, so That is next. All right, so that's our scheme. We're going to put some rectangles in there, build them in there like that, and then we are going to add up the areas of the rectangles. That's going to be the approximation to the definite integral, the area, net signed area there. All right, the next thing is, so that's the idea. The next thing is okay, we need to get some formula for the approximations. All right, so we know that our approximate area is the sum of the areas of the rectangles. Find the area of each rectangle and add them together. Well, so that would be the area of the first rectangle plus the area of the second rectangle plus and so on and so forth to the area of the nth rectangle. In my pictures I use 3, but in practice, right, you could use lots of rectangles. And in fact, right, the more rectangles you use and the thinner the rectangles become, the better approximation you're going to get, roughly. All right, for areas of rectangles, then we know there is a very simple formula for the area of a rectangle. It's length times width, right? So this would become the length times width of rectangle 1 plus the length times width of rectangle 2, and so on and so forth, right? And remember, the way we built the rectangles, we know what both the length and the width are, right? The length of the rectangles, right, would be, or the height, as we called it, would be f of x1 star. Those points that we picked and plugged them in to get the y value of the function, that's going to give us the height or length of the rectangles in each case here. And then the widths of the rectangles, right, were the widths of the subintervals that we picked. Okay, and so that's it. That's going to be our approximation. Add up the lengths and the widths, right, of those rectangles. Now, if you haven't watched the sigma notation video, you need to watch that because we're going to write this in sigma notation, right? In sigma notation, it would be the sum, I goes from 1 to n, f of xi star times delta xi, okay? And so remember, this sigma notation is just a compact way, right, of writing the a sum. So I just take this sum and write it in this. If you have trouble seeing that, then the easy way to see it is to write this in the expanded form, right? This is in sigma notation. What would you get if you wrote this in the expanded form? Well, in the expanded form, I would start with a 1, right? And I would plug it into I. So that would be f of x1 star delta x1, which is exactly this part right here. Then I would put a plus, then increase this to 2, plug that in. F of x2 star delta x2, and so I would get this, and so on and so forth until I stopped at the very last number right there. Okay. All right, and so this is the approximation formula. All right, if you had kind of wondered at all, where did the s come from in the integral sign, right? Well, remember, this is the Greek letter sigma, which is like a capital S, right? And f of x dx. So this is where the integral sign kind of comes from, right? It's almost exactly the same. A big S. This is just a Greek version, right? Using a sum, f of x dx. So that's kind of where that notation is reminiscent of. Right? Okay, so that's our approximation formula. In the next, there's more to this video, but in the next video, I'm going to show you an example of how to use this approximation formula to get an approximation. So make sure you take a look at that because that will definitely be on the quiz for this section. Okay, so that gives us an approximation, right? But what we want is not an approximate area. We want exactly the net signed area. We don't want an approximation, but as I already told you, you get better and better approximations by using more and more and thinner rectangles, all right? And so let's take a look at this demonstration. On Desmos here, I have a demonstration. And let's say we want the area between this function, okay, and the x-axis, so this blue shaded region. We want the area of. So I'm going to draw some rectangles in there. In this case, right, I have 4 rectangles. And over here I have a little slider, okay? And you can see there's some overlap and underlap when I use 4 rectangles with 5, 6, right? And now if I start increasing the number of rectangles that I use and make the rectangles thinner and thinner, right? Then you'll see I get a better and better approximation. And let's see, I don't want to increase this too much, but let's say I go to 50. You can see, right, that there is a very small overlap and underlap with the area of the rectangles in there. So as I increase this number of rectangles, I get better and better approximations. So what ends up happening is that if I take the limit as the number of rectangles goes to infinity, and also they have to get thinner and thinner as well, right, then what I will get is the net signed area, the exact net signed area. Okay. And so we talked about the definite integral, right? So this is the definition of the definite integral as Riemann gave it. Okay. So we have the limit of as the number of rectangles go to infinity, and they get thinner and thinner of this approximation formula. All right, so that's how people were able to calculate these areas exactly, and that was a huge, benefit, right, for people around in the 1800s, math and science. It turns out, though, that using this definition is to actually calculate things becomes very, very difficult. And we're not going to go over that, doing that by hand. I usually like to do that, but it's complicated, and there's a way around it. And the way around it is what we will talk about in the next lesson, which is called the fundamental theorem of calculus. Okay, and so that provides an easier method for calculating these areas here. Okay, but we will hold off on that until the next one. All right, so in the next video, which will be the last one in this section, I will show you how to use just the approximation formula to get an approximation.